3D printing. We're going to create this pair of Stanford Bunnies on a disk using a Mathematica program. This is the STL file. This is ready to be shipped off to a printer or print facility. The commands in Mathematica are relatively recent for 3D printing. But they seem to work pretty well. Pretty satisfied with the results. When we work with 3D printing, we're working with vector, vertex data, and polygon data, and that's what's used to generate the files that we call PLY files and STL files. Mathematica packages some metadata around the vertex data and the polygon data and calls that a graphics object. We can get graphics objects from the Mathematica through the example data, and this is the data for the space shuttle. We're going to use this what's called the Stanford Bunny. So here's the import of the Stanford Bunny. Shows that there are many vertex data, and the normals are not stored as such. They're actually inside the graphics 3D data set. So this is a rather long program, and the structure is actually in duplicate. You'll see things like A and B. In A, we are working with only the vertex data, and in the complementary 6B, we're working with the graphics data, which is both vertex and the polygon data. In general, I prefer to work with vertex and polygon data for the quality of the printed result, but for tutorial reasons and exploration of the data, I actually find it easier to work with the vertex data. It's easier to see what's going on, easier to work with the transformations. So this long program will work with both, export them both. The final result for the printer will come out of this for the vertex data. And Meshlab actually makes it work out okay. And the final result for the graphic object data, vertex and polygon data, will come out of this section. And according to the Mathematica testing, it actually is would be a successful print if we get to the printer. Okay, there's a lot of duplication in here. Let's go to this. Import the Stanford Bunny as a 3D. Where we see the 3D from this command. Properties, we get these commands. Defined the graphics object, so this is a variable we can use again to generate that image. Import the vertex, and we get that. We use the graphics object data to export a PLY file. The PLY takes both the vertex and the polygon data. We can see the vertex data here is this set of points, and the polygon is a listing of points. Okay, this is a kind of a complex file format. Let's take a look at a very simple one. This is a cube. So it's got 8 points and 6 faces. And you can see that apparently there's a point at the origin, and there is a face that connects 4 points. Let's take a look at that in Meshlab. I've already imported it. And that's our cube. So there's a point at the origin and faces. We can turn off the face view and see only the points, very tiny points, but they're the points at that end, the corners of that wireframe, and turn the face back on and see it like this. That means I can go to a more complicated PLY file and turn off the faces and see only the points. And we see the two bunnies, and faintly here the disc that they're sitting on. Turn back on the face and we see that. So this is the PLY version of that, and this is the STL. Both are the same. Two different renderers going on, but they're essentially the same images. So those kind of file types were exported from here. I do have a little bug in the connection between Mathematica and Meshlab. Mathematica tends to try to save file size by using some file types called unsigned character, listed in bold. Meshlab does not know how to read that. So it's a simple thing of going into an editor and changing the file type. Here's one of them. So I went into the editor. This used to say unsigned character or unsigned integer, and I just took out the U. So simple fix there. Then in the step 2, apply the vertex with list points, inspect vertex data. So we see vertex data. The vertex is, it's actually a very small object, just about a tenth of a unit. Now we pulled the vertex normals out of the graphic object. And I do want to show that even in this big Stanford Bunny file, the first 3 points are connected. First 3 points here at that coordinate are connected into a triangle. Points 4, 5, and 6 are connected in another triangle, and points 7, 8, 9 are connected in another triangle. So that's sort of the connection between vertex points, vertex data, and the normals. The normals are defining these triangles that connect points. The graphics object, the last time we saw it was without axes. It's easy to wrap some axes around it and label that. So get a more defined image. I'd like to get the object a little bigger and to put it in the positive octant. So that involves some affine transformations and some scaling. First, we're going to determine the minimum values among the whole list of coordinates. Remember, there's a huge number of points. So we're needing to find the minimum across all of these points. So I use a map thread with minimum across the vertex data to find the minimum, subtract it off, then a scale factor, divide by the scale factor, and shift a little 0.2. And now the smallest point is about 0.2 away from this origin vector, and the size of the object is about 1. I'd like to make another one, make a duplicate. Oh, sorry, here's the same thing with the for the graphics object. It's using the same mins and scale factor, and now we're using affine transformation. So here's the shifting, and here's the scaling of about 6-fold bigger. We have to take out of the grab the vertex data out of the graphics object. You can see it's the points again. Do the transformation on the vertex data, and then stuff the inside back into the graphics object, get the rest of the metadata, and that's our scaled object going from 0 to 1. Okay. Now I'd like to make a second bunny, a near duplicate bunny. So this one is kind of goes 0 to 1. I'm going to make another one that's in the negative x-axis, and it's slightly smaller. So I'm going to invert it along or reflect it in the xy. The determinant of this is +1, so there is no change in chirality. There's a 90% size, and this is a translation to get it pointed along the other nose to nose with the other bunny. So this is after all of the translations. This is the same thing with the graphics object, the original bunny. The translation is a slightly smaller and reflected bunny. Now we have to join the two bunnies together. It's a join command for this huge set of vertex data, and then plot them. Because there's so many points, there's 70,000 points, it gets to be spatially difficult to visualize. I'm plotting only 10,000 points. The graphics object with the two bunnies, this is actually a very simple join command showing the two bunnies put together. And again, I could draw axes around that. I'd like to put a circular base, so I need to find the midpoint. Midpoint is the average of x and y's. So there's the average of the x's, average of the y's, a little bit of a base thickness. So this is the midpoint for the top part of the disk, bottom part of the disk. Here are two disks with random point sampling to make a point cloud. And another join, and we have two bunnies sitting on a disk. The parallel construction with the graphics object. We make a base as a took a long time to find the midpoint. Make a base as a very thin cylinder, show the two, and we have two bunnies sitting on our base. So I'd like to take the vertex data, point data. Last time you saw it was as points. I'd like to take the vertex data and generate the polygon that wrap and connect all the points together. That's a requirement for the STL print file. So if I do the surface reconstruction of vertex data in Matlab, one of the commands is the list surface plot. If I do it only on the first bunny and do it on a limited number of samples, we see we got some artifacts developing. And if I do it on two bunnies, I'm even missing the original bunny. And if I do it on the bunny and the two bunnies in the base, the results are not satisfactory. But if we go into Meshlab, which has a somewhat better surface wrapping, this is the XY point file, 170,000 points. We do a normals, compute normals for point sets. What we're going to have right now is just a set of points. I dumped this up a little bit, I think. Preview. Okay, across the bunnies, I'm a little concerned about the quality of the discs. This may take a while. Across the bunnies, I'm still somewhat concerned about the disk. I'm not sure we've got a good polygon set for the disk. But the bunnies themselves, you don't see the artifacts on the ears that we saw with the Matlab surface reconstruction. Mathematica surface reconstruction. Okay, back to Mathematica. We've exported, the last time I worked with a graphics object, we exported the PLY file. We can import it again and do a test printout assessment, and that worked okay. This is over the Christmas holidays, and the service seemed to have been shut down for the holidays. This whole Mathematica program took just under 5 minutes to calculate on an old Mac Mini. So, pretty reasonable performance. All right. Thank you.